In this video, we're going to go over some of the properties of the cross product. So if you have three vectors, p, q, and r, and k as a scalar multiple, we have the property that vector multiplication is not commutative. We have the distributive law if you have p cross q plus r, that's illustrated here. And then we have the scalar law for vector multiplication. Note that they are different. And then we have the cross product of itself. So A cross A is the zero vector. So if we do an example of that down here, we had, just to show you that it's true, we have A cross A. So we're going to use our strategy that we did in the first video and write down our coordinates, starting with the second one. And it'll be the same for both because we're doing the same vector. And then if I start with my first coordinate, I'm going to get yz minus zy. That would be 0. Then I'm going to do the second coordinate, zx minus xz, also 0. And then I'm going to do the third coordinate, xz minus yz, also 0. Those three zeros together are what give you the 0 vector. So the next two examples that we're going to look at are talking about whether or not vectors are coplanar. So coplanar means that they lie all on a surface, so that you could draw all three vectors on a sheet of paper. What we're looking at is this product here, which is actually called the triple scalar product. And we're going to see what happens when we have coplanar vectors and then non-coplanar vectors. So in order to determine if the vectors are coplanar, if they are, that would mean that we could write A, B, and C as scalar multiples or a combination of the other two vectors. Okay. So what we're going to do is set up our relationship here, and then we're going to plug in our values. So here we are in 3 space. So setting up this equation, 4, 1, 1, t, 1 minus 8 minus 14. This is going to give us 3 equations with 2 unknowns. So 4s plus t minus 2 equals s minus 8t, and then 3 s minus 14t. Okay, so now what I want to do is I'm going to use 2 equations to solve for s and t, and then check and see if they are consistent in the third equation. So here, to start, I will rearrange for s. So I've got minus 2 plus 8t. If they are consistent in the third one, that means that my 3 vectors are going to be coplanar. So I'm going to carry on with my substitution. You could use a different method. It doesn't really matter. There are lots of ways to solve this system. This is one example here. And so when you solve this, you should get that t is equal to 1/3. Great. Okay. So now what we want to do next is we're going to solve for s. So that'll be our next step. So we're going to sub t equals 1/3 back into our equation 4 that we used to solve for s. So we've got minus 2 plus 8 times 1/3. And so what we have here is s equals 2/3. Okay. So now we've got a value for s and a value for t. What we're going to do is check and see if they are consistent. So we're just going to do a left side, right side check. And we're going to check in equation number 1. That's the one that we haven't used yet. So our left side of equation 1 is 3. And our right side of equation 1 is 4s plus t. So now I'm going to substitute in my values that I got for s and t. And I also get 3. That's great. So since my left side is equal to my right side, A, B, and C are coplanar. So now let's check the triple scalar product and see what we get. So the first thing that we want to calculate is B cross C. So we're going to use our same method from the last video. We're going to start with our second coordinate, and then our third, and then our first, and then our second again, just to help make sure we get all the pairs. Okay. So when we multiply, we're going to do 1 times minus 14 minus 1 times minus 8. That should give you minus 6. Then we've got 1 times 1 minus 4 times minus 14, which is 57. And then our last one, 4 times minus 8 minus 1 times 1 is going to be minus 32 here. Okay. So now we're going to add in our dot product. Hopefully you remember how to do that. So A dot B cross C is, we've got our A vector here as 3 minus 2 minus 4. And we're dotting it with our new vector that we found, B cross C. So minus 6, 57 minus 32. If you don't remember the dot product, you're just multiplying each of the components and then adding them together to get a scalar. And here, in this case, we get 0. Now this makes sense because if we do B cross C, we get a direction that is perpendicular, a vector that's in the direction that's perpendicular to B cross C. We know that A is on the same plane as B cross C, so that means a vector that's perpendicular to B and C would also be perpendicular to A, which makes the dot product 0. Let's try one more example. So here we've got another 3 vectors, and we're going to try and determine if the vectors are coplanar. Okay, so we'll start off the same way that we did before. We're going to set up our equation and substitute, zoom in a little bit, so substitute in our values. So we've got minus 1, 4, and minus 6. And then we've got minus 2, 1, minus 5, plus t, 3, minus 2, and minus 2. So this again is going to give us our 3 equations. And 2 unknowns, and we're going to use 2 of the equations to solve for t. So let's rearrange the second one again. That one's nice and easy to give us an expression for s. And then we're going to substitute our expression for s into our first equation this time. So we've got minus 1, minus 2, 4 plus 2t plus 3t. And we've got minus 1 equals minus 8 minus 4t plus 3t. And this will give us t equals minus 7. Great. Things are good. So let's solve for, go up here. Now we're going to sub t equals minus 7 into our first equation here. Well, I guess we should probably do it into let's use it into our fourth equation so that we can solve for s. So we've got s equals 4 plus 2 times minus 7. 4 plus minus 14, s would be minus 10. So great. We found s and t using 2 of the equations. Now we're going to check using equation 3, the one that we haven't used yet. So it's a simple left side, right side check. So the left side of equation 3 is minus 6. Our right side is minus 5s minus 2t. So if my vectors are coplanar, I'm expecting that I should also get minus 6 on the right-hand side. Let's see, plus 50 plus 14 would give me 64, not equal to 6, which means that my vectors are not coplanar. So I can't lie them on a flat sheet of paper. So let's look at the triple scalar product again. First thing that we have to do, just like the example before, is B cross C. So same approach, we're going to start with our second coordinate and write them down. Same thing for C. Hopefully you're starting to get familiar with the cross product. So here, our first coordinate would be minus 12. Our second coordinate would be minus 19. And our third coordinate would be positive 1. So now we're going to dot that with our A vector. So we've got, fit that in down here, A dot B cross C is going to be minus 1, 4, minus 6, dotted with minus 12, minus 19, and 1. When you figure this all out, you're going to end up with minus 70, not coplanar, triple scalar product is not 0. Let's summarize that on the last slide. If you have vectors in 3 dimension, A, B, and C, if the triple scalar product is 0, then the vectors are coplanar. If the triple scalar product is not equal to 0, then the vectors are not coplanar. So the triple scalar product is also the volume of a parallelepiped, which is just kind of a cool fact. But you can also use the other arrangements. Okay, sort of like the cosine law. It's better to memorize the spirit of what the triple scalar product is rather than the actual letters that go with it, because it helps you to make better conclusions. So let's just add on, this is the triple scalar product, which can be used to find the volume of a parallelepiped, which is right here. And you can see, so if you had vectors that were coplanar, so if this vector C right here lay on the same plane as A and B, your volume of that shape would be 0, or your triple scalar product would be 0. As soon as it is not coplanar, you end up with a shape that has volume. Good luck with the applications of cross product.